All right, so again, we're going to start by looking at the general shape of a rational function. A lot of rational functions have the same general shape. There are some exceptions, and we'll go over those. But generally speaking, they're looking like hyperbolas. So if you look at the middle graph here, the middle graph is our best example of a hyperbola. You have your two dashed lines, you've got your y-axis, you've got your x-axis, and then you've got these curves on both sides. Okay, you've got these curves on both sides. If you know about a circle, imagine taking a circle, okay, cut it down the middle, and then watch my hands. Flip them out like this. So take a circle, cut it vertically, and then open it up. And you get something that looks reflected. Similar to this, if you look at an angle. If you were to take these and reflect them both in, if I were to reflect this one in here, and if I were to reflect this one in here, I kind of have like almost like a circular shape or an ellipse in the middle there. So a lot of these shapes are really like ellipses, okay, an ellipse, cut in half, and then open it up, unfold it in each direction. And what you'll get something like this on both sides, okay? That's what the general shape is going to look like for rational functions. You're going to see a lot of them. You're also going to see some other weird looking stuff, and we'll discuss how they look different for each one, depending on different properties. So the first graph here, you have 3 parts to the rational function. The second graph, you have 2 parts, but then the third graph, you have 3 parts again. The amount of parts of the graph is indicated by however many of these vertical lines you see. See these vertical dashed lines that are blue? Okay, those are called your asymptotes. And this is a very, very difficult topic to understand if you don't listen carefully. Because an asymptote is not something you've heard before. But I can start by giving you a very, very simple example. If I asked you to walk to the door from right here, can I get a volunteer to come do this? From right here, and so what I'd like you to do is walk halfway to the door. Halfway only. And then stop and you get halfway. Okay. So that's halfway from her. Now, walk halfway from there. Walk half of that now. Okay? Now walk another half of what's left now. Okay? Now walk another half of that. Now, eventually, what's going to happen, right? She theoretically won't ever make it to the door because she keeps cutting her distance in half. So she's going to keep getting closer and closer. But realistically, what's going to happen? She's got to get to the door, right? So the idea of an asymptote is this. The idea of an asymptote is that you approach something, but you never really get there. You never really get there. So imagine if you had a radioactive element, and you have this rock of uranium-238, which is radioactive, and it has what's called a half-life. Who remembers what a half-life is?
No, it's like after carbon dating.
Okay, carbon is an example, because carbon dating uses radioactive half-life. It's an example. But what is a half-life? I heard you talking, sorry.
Something about how much radiation gives off.
Good. Or, not gives off, but it actually does give off, or what's left over, really. So, imagine you had a rock of 20 kilograms, and it's uranium. And its half-life is 5 years. What that means is after 5 years, it will have half as much radiation. It's not going to actually deteriorate. The full rock is still there. It's still a 10-kilogram rock. But only half of it, theoretically, is radioactive, or it's half as radioactive. After another 10 years, or whatever I said the half-life was, 10 years? 5, sorry. After another 5 years, it's going to be half of that. After another 5 years, half of that is radioactive. So it's always going to be radioactive, because you keep half. Go in your calculator right now. Everybody take out your calculator. Type in the following. Type in 1 divided by 2 and hit enter. Right? You should get 0.5. Again, 1 divided by 2, enter. Then press again, divided by 2. And then keep pressing enter. What keeps happening?
It gets lower and lower.
It gets lower and lower because you're what? What are you doing to it?
Divided.
You're dividing by 2 or you're halving it. But what do you notice?
It never reaches 0.
It never reaches 0. Eventually, you're going to start seeing e to the negative. Okay, just keep it answer. Just keep it answer instead. After that, after the answer. You're going to eventually see e to the negative 11, or e to the negative 12, or e to the negative 100. E to the negative just means scientific notation. So you're talking about a number that's like .000000005, or 00000 with like 30 zeros and a 2. But there's always going to be some fraction of the radioactivity left over, because it's only losing half of its radioactivity. So it's never getting to 0. And you can keep going forever. And I see you two, you're having a race over here. You're at negative 20. He's at negative 14. She's beating you by half. I'm at negative 60. 69, 70. Okay,
What's impossible?
Eventually, either A, you're going to break your calculator, or B, it might give you an error because the number gets too small to evaluate. But the idea is that you're getting smaller and smaller and smaller. No! Because you get to the error, you cleared it?
That's what I
Enter plus?
Just go to and then
Yeah, you could just go 2 and hit divide by 2 and redo it. Anyway, the idea is that you're never going to get there. So, what's going on here is the following. When I look at this graph, I'm going to follow the graph with a green marker right now. I start here. As I get closer and closer to this value, which looks like it's 3, or negative 3 right here, because that's negative 2, and that's negative 4, my graph gets closer and closer and closer to it, but it's never going to actually get there. It's never going to get there. It's going to get what's called asymptotically closer, hence the name asymptote. So this green graph, it keeps getting closer and closer. And what I can do is, I can show you a very simple example of this. Because you need to know graphically what we're doing. Because what we do in a minute is not going to make sense if you don't know what's going on here. So a simple example of this would be for me to type in a rational function. So I'm going to start by saying f of x. Remember, rational functions are a fraction. So you have a function over another. So f of x equals parentheses 2x plus 5 over parentheses 3x minus 4. Enter. Okay, so I look at this one, and I'm going to see, and I happen to know what the value is. I'm going to say it's x, and you'll know in a second how to do this. Let's say 2/3. Oops, it's not x, but y.
Mr. Howard, let's go there. Mr. Howard, let's go there.
You got the 0?
I got there first.
Now, you actually started, you just kept going all the way out there?
I did it first.
You did it first? You have the calculator out.
I used Danny's.
Use Danny's?
I'll do it.
Okay. So for this problem, you have, again, tomorrow we're going to go into horizontal asymptotes. Today is just about the vertical. So for today, you have this line. It's an imaginary line. It's not really there. Okay? This line that really splits the graph up. A portion of it is always on the left side of the line. Another portion is always on the right side. And that was what we looked at for our smartboard for the middle example there. So what I'm going to show you now is this. It looks like this is going to get closer and closer here, right? So if I move up, it looks like this graph, and watch it. This, let me show you 2 different colors so you can see the difference.
Yellow.
You can't see yellow, sorry.
Red.
orange,
Really?
tangerine,
Black.
lavender,
Black.
lavender,
Black.
Okay. So this is the actual, this is the actual curve here, the solid black line. The dashed blue line is the vertical asymptote. And it looks like it's getting closer to it. And if you move up, eventually, it actually looks like it is actually on it, right? It looks like it actually matches up. But if I go here, and I zoom in on this, as I zoom in further, what do I notice there is still? There's still a gap there. And if I keep going up, and keep going up, this gap doesn't go away. And if I zoom in even further, it looks like the gap is even bigger. Even though I'm going from 1.2, this is 1.2, all the way to 1.6. So look how zoomed in I am. Look at your x values. 1.2 is the x, and then the 1.6 is the x, which means that really, right now what I'm doing is, this is 1.2, oops, this over here is 1.6. So this is 1.5, 4, 3, 2, 1.1, nope, I'm going by 2s, or 0.05s. I'm trying to estimate, sorry. There it is, okay? So every 2 vertical lines only represents 1/10 of a unit. So we are really zoomed in right now. We see that little gap between the actual function and the asymptote here, this gap here is only about 0.05. Again, because from here, from one box and then to 2 boxes over, that's a gap of 0.1. Everybody see that?
Yeah.
But what my gap is really is pretty much 1 box length, which is actually 0.05, because that's half of that number. Think of this as 10, right? 0.10, half of 10 would be 5. So the gap that we see that exists between the actual curve and the vertical asymptote is so minuscule, but it is existent. It does exist. So this curve will never actually get to the asymptote. It will approach it asymptotically, meaning it gets closer and closer, but it's never going to get there. Now, this is a term that you're going to continue to use in pre-calc. It's called a limit. So this has a limit. The graph, eventually, the limitation will be to whatever this vertical line is, this vertical asymptote, which is at 1.33333 repeated, or 4/3. And I'll explain how to figure that out in a minute. We'll go through how to get this number. But what I want you to recognize is that this is really what's called delta x, this gap. And what's happening to delta x? It's getting smaller. So a vertical asymptote, okay, one way of thinking about it is when delta x goes to 0. Delta x gets smaller, or it goes to 0. That's when you really have a vertical asymptote. When the distance between the curve and that vertical asymptote keeps getting smaller and smaller and smaller, you get to something called a limit. Okay? So delta x is getting smaller or going to 0. So a vertical asymptote can be thought of as delta x going to 0 or getting smaller. That's an arrow. Sorry, let me blow it up for you. Okay, like that. Delta x goes to 0. Okay? Now, this is not something that your SAT is ever going to ask. Okay? But this is stuff that if you ever want to study for calculus or calculus, you got to start using this terminology. Because you're going to see it next year, and then when you get to calculus, you're going to use it left and right. Okay? Limits are used in everything in calculus. It's the first, there's 5 chapters in calculus. First chapter is limits, which is what we're really doing right now. The second and third chapter are called derivatives, and the fourth and fifth chapter are called integrals. And they're different types. But this is an entire, like, fifth of the year, really. You spend almost, well, not a fifth of the year. You probably spend about a month with calculus learning the idea of what a limit is. And you've already been able to get a little preview of that now. Okay? All right. With that said, let's go back to our notes to continue discussing the general shape of graphs. So looking back at my notes here. In the graph at the left, I'm going to notice that there are really 2 vertical asymptotes. One here, and then one here. In this case, those vertical asymptotes happen to be at -3 and +3, which are symmetric. That's just a coincidence there. Okay? Over here, I see that there's a vertical asymptote around x equals 1, and over here, I've got a vertical asymptote at x equals 4, and at x equals 0, right down the middle there. Which x equals 0, you know, is the y-axis. Again, this is x equals 0, this is your x equals 4. Remember, vertical lines are x equals. What are horizontal lines? Y equals. Again, some number there. What else could I call that vertical asymptote that you've used before? What is another term to call that? Where it splits up part of the graph?
Oh, 0.
What does it start with?
A D.
Domain.
Okay, it's a domain restriction. That's one way to think about it, because the domain exists everywhere except at these gaps. So the domain doesn't exist at -3 and 3 for the first graph, or the domain doesn't exist here for the second graph. That's a good way to think about it. Domain restriction. That's another word I was thinking of. Not derivative. DI.
Oh my gosh.
Discriminant.
You've used the word before in Algebra 1 to indicate where, if I'm following the graph, to get to the next part, I need to pick up my pen and continue.
What?
We used it when we did domain and range this year, when you had the functions with the open circles. What were those called?
Bisect.
They were not included, good, but I used the word, guys. That's where vocab comes in. Because if you didn't write it down then, make sure you do now. Starts with dis. Dis is something.
Displacement. No.
Discontinue.
What is it?
Discontinue.
Discontinuous or discontinuity. Very good. Remember, guys, for something to be the word continuous, it means that it flows, right? Like a river. But if you had a dam in the middle of the river, what would it cause?
Well, for water to stop, to be
It would cause the water to kind of stop, go slowly through it, and then go through, right? Causes that slowdown. Now imagine, though, if in a river, suddenly you had this big canyon in the middle of the river, and the river fell off, which would be then a waterfall, really. But then imagine the river started picking up again. So you've got a river with a giant hole in it. I know this is not realistic, okay? With a giant hole in it where all the water fell into. And then somehow the water continued on the other side. You would call it like a big hole in the river, right? Or a gap. A gap in the river?
Well, a black hole.
Imagine a bridge. Imagine a bridge that's being built. Have you guys seen the movie Speed?
Yeah.
With Keanu Reeves and Sandra Bullock, and they're on the bus.
Aren't they all in the same?
It's from like the 1990s or 1980s. Really good, but it's on like it's on AMC or some of those random old channels. But it's not- Showtime, yeah, it is on channels like that. Yeah. The idea of speed at one point, they have to jump a gap in a bridge. They have to get up to enough speed to actually launch across the gap in a bus. Physically, it's not realistic. I've done the math on it with a class of mine. It doesn't work. In physics, if you do physics, we'll talk about projectile motion and how that was not really possible.
Just the weight of the
because of the weight and the incline they were at. Physically, it was impossible. But again, it's a movie. Now, the idea we're going to look at today is we're going to say, if I ever trace a graph and I have to pick up my pen to continue, it's a discontinuity. So here, if I use this graph, watch. I'm tracing it. I'm going to keep going up forever, aren't I? To start up on this point down here, I have to now, come on. I have to now pick up my pen, start up again, continue, go down, pick up my pen again, continue, and then continue on the graph. I had to pick up my pen once and then twice. So there are two discontinuities here. Again, for the middle graph though, watch. I go through the graph, I go down, I'm going to go down forever. I have to go on the next part, I have to pick up my pen again and continue up here. So how many discontinuities are here? Just one. Just one in the middle graph. Because there's only one vertical asymptote, so there's only one discontinuity. For the third graph, watch this. I go down forever. I go down, keep going. To continue, I have to pick up my pen, start up here. Go down to my cubic looking function. Go down forever again. Pick it up again. There's two. And then that goes forever. So I have two discontinuities. Because there are two vertical asymptotes. These are going to, guys, the tail ends are going to go on forever. They will go on forever. But it's the amount of times I had to pick up my pen, and it was two on the last one.
So having the two vertical asymptotes, it also tells you how many
You have discontinuities. There's another type of discontinuity we're going to talk about after we do the first example, which is called the hole in the graph, which is like you guys would see the open circle with domain and range. The hole in the graph indicates another discontinuity, different from vertical asymptotes, and we'll be able to distinguish between the two.
the number of the discontinuities is practically the same thing for the vertical asymptotes.
And the holes together, because we don't have holes here. But if I had a hole, Julia, imagine there was a hole in the graph right here. It was an open circle. I would have to go start the function, lift my pen up, go over the hole, and continue. That's one extra discontinuity, isn't it? So this graph would not have two discontinuities, but three discontinuities from the third part, which would be the hole. So a hole in the graph also indicates that. Okay? A hole in the graph.
Two.
Now, we want to go to the next part and take a look here. And remember about my domain. Remember from the last concept, what restrictions did I have to set on my domain based on the problem? What did I have to look at? What part of the fraction?
The denominator.
The denominator. Good. The denominator. Whatever makes the denominator 0 makes the fraction undefined, which in my mind which in my mind is a restraint to my domain. Well, if I go back to my last example and I look at my domain for these functions, wherever I have to pick on my pen, there's no domain. So there was no domain at the hole. There was no domain here at x equals -3. There was no domain at x equals +3 because, again, those are holes or they're gaps in my graph. So my domain restrictions are really the same thing as my vertical asymptotes and my holes. So take a look at this example and tell me what the domain restrictions would be for this rational function. I know some of you know right away by looking, but show me mathematically how you would solve for the domain restrictions. What would you do? Very good, Victoria. Take the denominator and set it equal to 0. Set it equal to 0. Excuse yourself, whoever that was.
Oh, no, wait, no, I was.
Is that not a verb?
No, it was the verb.
It really sounds like a verb. So 3x minus 6 equals 0. That will cause the function to be undefined. By default, as Anthony said here, all we do is solve. We get x equals 2. X equals 2. So, for this graph, at x equals 2, I have a problem. There's an issue with the graph. I need to figure out what that issue is now. Okay, again, there's some sort of an issue with the graph at x equals 2. What is it? And I don't know right away. It could be a hole, or it could be a vertical asymptote. And there are ways to tell, and there are rules we're going to go over. But in case we didn't know the rules, the easiest way is to start by looking at a table of values. So I want to know what's happening near x equals 2. So what I want you guys to do is this. Construct a table.
I'm in a box.
Okay? X and h of x. And what I want you to do is I want to pick values to the left of 2 to see what's happening to the graph as I keep increasing it. So I want to try, like, for example, I'll use the numbers that I happen to use here, just so that we're consistent with the notes. Okay, 1, 1.5, 1.8, 1.9, and then 1.99. Oops.
Mr. Krusty Krab. Huh? Mr. Krusty Krab. Is this the Krusty Krab? No.
So, first of all, somebody please tell me, why didn't I put 2 in the table?
Because it couldn't work.
Because why? Why?
Because it's the restriction.
Because it's the restriction, because it makes it in the denominator, which makes it undefined. Again, you can't plug a 2 in here, so we're going to try numbers that are getting closer and closer to 2. This is, again, where limits come in. Remember that delta x? We're getting closer and
Is
closer.
that 1.99 or 1.9 colon?
99. Sorry, 99. So I'm just adding a 9 to the end of it. Okay, sorry, I was writing on a tilt while on the board. Now, go to your calculator, please. Type in the function, please, in your calculator. Go to your table, type in those values. Show me what you got. Watch. You can't see it, but what you could do.
Wait, you always been there. Wait, no time will be one for That's on the one.
Let me think about it. There's got to be a way. I'll think about it. I don't
You
know.
ain't no
Some calculators, the older models, like whenever there was a rational function, they would put the line in there for you to show you the asymptote. But it was confusing a lot of students because they thought it was part of the graph. They thought the graph looked like this, like it was cusps.
Well, according to this thing,
They thought that's what it was, but it's not. It's not doing that. But you kind of want to see like a dash line there. It just doesn't show it. There's got to be a way. Let me look it up. I'm just going to Google it so you can do the same. But let me look it up.
No time.
Okay, on Julia's calculator, like when you type in the exponent, it comes up with a little square.
Because hers is under a different mode. If you go to mode, you want it like that? No. then don't worry. But it's under mode all the way to the bottom. It says math print or classic. You're on classic, she's on math print. Doesn't matter, whatever you're used to. I use classic forever, but if you use math print, you're used to it, go all the way down.
I am.
You really was.
I really was.
You really was. You really was.
No, I really was.
Don't try to be cool. Don't try to be cool. You keep looking at the face right now. That's how.
Oh wait, we're not being never bring back some cupcakes. You're just gonna bring back some cupcakes.
Just right.
Cupcakes for what?
So you're gonna bring some more cupcakes yesterday.
It must
I
be a
didn't say we
different,
were going yesterday.
Yeah, you said when you get home,
Mine's
you're
like
gonna
5
make
years old.
No.
that's fine, the newer ones only have, that's fine. Okay, because they came out with that on the giant
Oh.
spires, Jason.
Gosh.
These
Okay.
ones, the newer ones
Sorry.
came in.
So
So that's.
What's your funny fact?
Yeah, got it.
Math print helps us with actual parentheses.
You're blood.
Up to you, try those.
They're out there.
He said he didn't.
When are you gonna? Oh, you fall. Downstairs.
When do you need to bring them out? When you bring them out, then get back to me.
You like tighten it up on
Bring them out. So bring them out and then get back. They actually probably do it during the school day, get back to you. Come back after school today. Now, what are our values here? Can I get somebody to raise their hand? Tell me, if you disagree, right away, please raise your hand if there's any disagreement with us. Go ahead, Derek.
Negative 5.333.
Everybody disagree with him there? What did Derek do by accident? Did you put parentheses around your numerator and your denominator, Derek? It's not just you, it's probably many others, so you're helping people, dude.
Yeah, man, you are.
Guys, when you type in a rational function, I told you this once already, you need parentheses around your bottom and your top. Derek, change your y equals, go back to your table, and then tell me the new numbers.
Okay. I got it. Alright, I got negative 0.667.
Good, I'm gonna round.
And then for 1.5, negative 2.
Go ahead, keep going.
8, I got negative 6.
Wait, negative 2 what?
Oh, it's just negative 6.
Okay,
And then for 1.8, I got negative 6.
keep going.
1.9, 12, negative 12.67.
Good, keep going.
And then for 1.9, I got negative 132.7.
Very good. Okay. Now, people, think for a second. You can easily look at the graph and see that there's a vertical asymptote. Everybody hit graph, please. Look at the graph. You'll see that it's not on your graph, but the vertical asymptote is imaginary. It is there.
How do you read?
I'm going to try and see if there's a way to graph vertical lines. I don't know how to do it off the top of my head. Does anyone know how to do it? Okay, let me look it up. I'll get back to you. I'm not sure how to graph a vertical line because the equation is really x equals 2. That's the equation of the vertical line. That's the asymptote. But you can't graph a line that says x equals. It only says y equals. So I'm not sure how to do that off the top of my head. I've never tried it. I was telling Victoria, a lot of old calculators used to put the asymptote in there for you. But a lot of students used to think that it was part of the graph. They used to think that the graph looked like this. It would curve down, go up, and then come back down. But that's not the graph. It was a vertical asymptote, but it confused a lot of students. So on the new calculators, they stopped doing that. If you have an older calculator with you right now, you might see a vertical line there. Anybody have a vertical line on theirs? You have one on yours. Do you mind if I show? Thank you. It's the 83 plus has it. So if you have the 84, you don't see this vertical line here. Again, take a look, please. You're not going to see that vertical line there on the 84. The only ones the 83s had them for a while, but they took away, look, did away with it because it caused a little bit of misconceptions. And so again, you don't see the vertical line on yours right away. Thank you, Daniel. Appreciate it. And it's not better or worse, it doesn't matter, but you got to know this there. Now, here's what I want to do next. Try and graph those points, please. Try and make yourself a sketch. Just draw a quick XY axis, please, just like this. And look at where those points would be. You're looking around positive 2. So call this 1, call this 2, and call this 3. And please, think about your y-axis before you do this. You don't have to label your y-axis, but look at the magnitudes of the numbers. Try and graph all those points, please. It's tough. It's not easy to graph this kind of thing. But you don't have to label your y-axis. Just estimate where the points would be. Label your x-axis like I did, please. But for the y-axis, all you're going to be doing is estimating where the points are going to be.
What do you find it
So the
Negative 0.7.
I got negative 0.7, negative 2, negative 6, negative 12, negative 132. I'm rounding to the lower number now. If somebody finishes and wants me to look, please raise your hand. I'll come take a look. I'd like somebody to come up and put this one up.
Would it be in like some sort of stepping stool?
Say again?
Well, what I would like to say is that
It's going to get lower and lower.
God is good all the time.
That's a very good example of that. Use the red marker. I'm going to put your asymptote in at 2, okay? We already know there's an asymptote from the graph because we looked at it. Julia's going to come up and sketch where her points are. If you finish that, try the same thing from the other side of 2. So try another table and use numbers like 3 and 2.5 and 2.2 and 2.1. You can feel free to try from the other side also.
According to my calculations,
Why did it go so far? Oops.
It's not very synchronized, right?
No.
No, it's just a big secret.
Remember, you can't touch the axis, right? You can't touch the asymptote. You guys ever seen like,
Can you do that?
students will do like math videos as extra credit or as projects? They have to like rap a video or sing it to
Mr.
like,
Williams always
students
shows
and
us
stuff.
rap.
Mr. Williams shows it
I always do it in college. There's a lot of good ones. I like that. The vertical asymptotes. Copyrighted. So obviously use the song Can't Touch This, but find a way to change the lyrics to that to talk about asymptotes. But you're gonna have to learn more about them first. But keep that in mind. That's a good one. So here we go.
Okay, mathematics.
Julia's graph is a great example of this. And what she noticed is this. The graph really, what it does is it dives off. It curves off down toward the asymptote. Again, her points were here. Her point was here, 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 and here. Those were her 5 points. And none of them are touching the asymptote, even though they're getting closer and closer.
Wait, is the last one in 0.1 or 1.999?
1.999.
Oh.
1.999.
No, I'm just confused.
Because what we're doing, Ashley, take a look at the pattern. We're getting closer to 2, aren't we? So 0.19, wouldn't that get further?
Yeah.
So think about it logically there, but I understand the misconception. Keep that in the back of your mind, okay? These numbers are getting closer to the goal, or the target. Guys, 2 is the target. When you get to calculus, you're going to start thinking about 2 as a target. You're trying to hone in on the target from each side.
Oh, actually touching it?
So in this, without actually touching it. So on this side, try now, please, on your own.
I'm sorry.
Please fill on the table on your notes and draw yourself a sketch on the other side now. Again, fill on the table. Use your calculator, please. And then graph the points on the other side.
I don't even know what equation we use. Can you please highlight the equation number?
Yeah, we're going back to that.
Put that in y equals.
But I keep putting in the y equals and I get different answers.
Do you have parentheses around your numerator and denominator?
Check these out.
I went over this. He made the same mistake. You gotta listen, Jason, please. Go to your y equals, all right?
Yeah.
Put parentheses around each of them. And then go back to the table and look at your numbers. They'll be the same as these over here. Guys, parentheses are so important. Any rational function needs parentheses around the numerator and the denominator, both.
Two equals stupid.
No.
I heard 2 equals stupid.
No, No, that's the y value.
I said, you can. Oh.
The x value.
Yeah.
That's right. That's right.
1 plus 1 equals.
Go to your table. Type them in.
4 plus 4 equals.
I already knew that.
Type over.
4 plus 4 equals.
Type 3. Oh, where did they come from? You said, how do you get the values? The values, by the way, Julia, always indicate the y value. So that you're asking how to get these values. You meant, how do I get these points or these locations? What I'm trying to do is I'm picking points to the right of it, and I chose those points. And what we're doing is, we're looking from the left and from the right. If we hone in on it, we're honing in on what's happening to my graph. So I'm just picking a number to the left or to the right. In this case, it was to the left. 1 was to the left. Now I pick a number to the right, and I get closer and closer to 2, but without going to 2.
Stop. How many times?
You can use your, we're going to do enough of these that you're going to notice the pattern, that you always start maybe with the integer before, have it, get closer, get even closer, get really close. Okay?
So you won't always give us the numbers?
These numbers, after we do enough of these, you'll realize what numbers to choose. Because all I'm doing is pick up the patterns. I went 1 to the left, and then I picked numbers that were closer to 2. I went 1 to the right to 3, and then I started getting closer to 2. You're always going to get closer to the target, which is the discontinuity. Can I get a reader for these 5, please? Read me their table.
Okay.
And
2, 3.33, 7.33, 14, 130.
agreed? Okay, you want me to plot it? You guys want to plot it? Somebody want to come up and show what they would think? It's a tough part to do. How would you plot this on the other side now?
It's like you have to make the y-axis longer with the positive side.
Okay, I mean,
It's opposite.
sure, we could always do that. That's fine. But it's what? What is it really?
It's the opposite.
It's really like symmetric across the
Oh.
side, right?
It's flipped and inversed.
Okay, so 3, 2 would be like here, right? Then I go to 2.5, and I get up to 3.3. All right, that only goes a little bit up. Then when I get to 2.2, I jump to 7. Jumps a little higher. Then what I notice is, the minute I get to 2.1 and closer, I get to 14 and 134. So this is shooting up, isn't it? Sure. It really is. It's growing exponentially almost here. So I'm looking here, and my graph looks like this. But again, what I notice is, it's getting closer and closer to the asymptote. But everybody, please, type in 2 now in your calculator. Type in 2 for x. What do you get? Error. Because it is undefined. X equals 2 is undefined.
Why?
Look, man.
Why?
Oh, there
Why?
Because you keep trying to ask questions to ask.
So this is what we had, really. Okay, we filled in our table over here. We filled in our table in these 2 spots. This is the actual graph of what it looked like. Okay, if you zoom in on your calculator. Now, stop, Jay. We know that in this case was a G or H? H? Yeah. H of 2 is equal to 4/0, which means it is undefined here. Okay, again, that's what you just did in your calculator. If you plug in a 2, the calculator responds with 4/0. Well, 4/0 is undefined.
Well, where's the 4?
Look at the actual problem, guys. Plug in a 2 here. Plug in a 2 here, you get a 4. Plug in a 2 down here, you get a 0. 4/0. Now, here's a conclusion I want you guys to write down, please. I'm going to read it once. Obviously, tomorrow we're going to continue this concept. We still have half of it to do.
I still got your spot.
From this example, we can see that the values, okay, values with S in parentheses because there could be more than one vertical asymptote. We can see that the values of the independent variable that cause the denominator to become 0, which is what we were talking about, in this case x equals 2, are not included in the domain of the function. The values that cause the denominator to become 0 are not included in the domain of the function. This means that there must be a discontinuity, such as a vertical asymptote. There must be discontinuity, such as a vertical asymptote, either at that location or just there. Let's change there to at that location. That sounds better.
Is Mark looking something?
There's another type of discontinuity. Again, we already talked about it, but we're going to look at now in example 2. In example 2, and that's called a hole. We're going to stop for today because we're done with time. But tomorrow we'll pick up with looking at a hole in the function. One thing I do want to write is this before we exit for today. We have about 3 minutes. I want to write the domain for this function. So once everybody finishes this, let's just list the domain because we didn't do that. I meant to do that before. So for this problem, this was the graph that we had here. And I'm just going to sketch it real quick.
Well, wouldn't it be a union of?
Yes, very good. The union of?
The negative infinity to positive infinity to positive.
Okay, close, close. You made a little mistake with your statement, but it's union. Trayvon started by saying it's got to be a union of two things, right? Remember domain? Union of? Union of indicated that there was a gap. Well, where's the gap in this problem? At 2. So you go all the way from negative infinity, all the way to 2, and then we start up again at 2, and we go all the way to positive infinity. But there's a gap at 2. Again, because there's arrow tips on these, remember. There's a gap at 2. You said infinity, that's fine. Another way to represent this, another way to represent the domain for this example that we just did, would be to say that, and this is a little bit different, x is in the set of real numbers. This is called set notation, and you'll learn more of it next year in your preview. X is in the set of real numbers such that x cannot equal 2. So it means x is all numbers, that's what this says, x is all numbers that are real, so not imaginary, but it can't equal 2. Okay? I prefer the second way for myself because it's easier for me to remember, but you use this way a lot more in pre-calc and calculus. Okay?
Yeah.
Is it what?
No, with the.
That's E, and then it's like a double slash on the R. Where's my marker, guys? The green one. Here it is. This is like a bold. Imagine like a bolded R. It's like a double. There's a double slash on the R. Okay, imagine like a bolded R like that. That's what that really is. So again, this is called interval notation, and finally set notation. Okay, you guys have tonight off from homework. I'm going to wait till tomorrow to give it to you. Okay?